Okay, hello. I'm very happy to be here. I'm going to talk to you about Morse-Bott, embedded contact homology, and Cascades. So I'll first give you a review of embedded contact homology, then I'll describe how Morse-Bott theory works in the holomorphic curve setting. Then I'll tell you about how to count cascades for ECH. And in the end, I'll give you some sketch of the gluing results, which is kind of the analytic engine that goes into this story. So ECH, in very brief words, ECH, it's a floor theory with generators, Rabe orbits, and differential defined by counting pseudo-holomorphic curves. So suppose you have a contact 3 manifold with contact form lambda. So the Rabe vector fields are uniquely determined by these conditions. And we consider the periodic orbits of this vector field. We call it the Rabe orbits. And we require lambda to be non-degenerate. So means given a Rabe orbit, the linearized return map does not have 1 as an eigenvalue. This is kind of a technical condition, but for us, this means all the Rabe orbits are isolated and discrete. So then that's for the Rabe orbits. So where do we count holomorphic curves? We have the symplectization, which is R cross Y3 with symplectic form given by this. And on this symplectization, we choose a generic almost complex structure compatible with the lambda in the usual SFT sense. It means that it's invariant in the R direction and it preserves the contact structure and sends the symplectization coordinate to the Rabe vector field. So the generators for the ECH chain complex over Z2 coefficients are given by orbit sets. So it's a collection of embedded orbits alpha I with multiplicity mi, non-negative positive integer. And the way ECH talks about multiply covered orbit is by giving an embedded orbit with a greater than 1 multiplicity. And the differential is counted by holomorphic current in the symplectization. And the J holomorphic current is given by a collection of, is there a laser or I can just point? Okay, I can just point.
Right above the clicker.
Oh, okay. Oh, there we go. Excellent. So a J holomorphic current is a collection of Ci, which is a somewhere injective J holomorphic curve, and Ni, which is the multiplicity. So in ECH, how do we talk about multiple covers? We describe it as somewhere injective curve with higher than 1 multiplicity. So I've told you what the Rabe orbits are, generators are, and the holomorphic currents are, and how do they talk to each other. So suppose you have an orbit set, we talk about the convergence as currents. We say a J holomorphic current is positively asymptotic to alpha if the following condition holds. So if you take, as S becomes large, you take the slice Y cross S cross Y3, which is a copy of the contact manifold. The intersection of this holomorphic current is a one-dimensional set with multiplicity. And this one-dimensional set with multiplicity is required to converge to alpha, which is the orbit set, as a current. To make this slightly more precise, what do I mean by convergence as a current? It's the usual kind of geometric analysis sense is that for any one form in your 3 manifold, the integral of this one form over the intersection of this holomorphic current counted with the multiplicity on this slice converges to the integral of this one form over these collection of Rabe orbits with multiplicity. And this is what it means to converge as a current. And there's a similar notion for being negatively asymptotic to an orbit set. And this is the only way we'll talk about in ECH. We'll talk about how holomorphic currents can talk to J holomorphic currents can talk to periodic orbits. It's convergence as currents. And to give an illustration of this fact, so let's say C is a somewhere injective curve, has 2 positive ends, and each asymptotic to the simply covered Rabe orbit gamma. As I've drawn here, this is C and this is a Rabe orbit. Then C1, which is the somewhere injective curve with multiplicity 1, is positively asymptotic to gamma 2 with multiplicity 2, because as a current, it covers gamma twice. And analogously, C2 is positively asymptotic to gamma 4. And I should say at this point, there's more than one way for which a holomorphic curve can be asymptotic to a current. I've drawn one way here, which is you have two ends coming in, each with multiplicity 1. Another way is you can have a single end that comes in with multiplicity 2. And that's also asymptotic to gamma 2. Okay. So I have some J-holomorphic currents and some orbit sets. How do I count them? How do I make sense of a differential? And this is done with the help of an ECH index. So given a pseudo-holomorphic current, I can assign to an ECH index IC, which is sum of three terms, Q tau, C tau, and mu tau ECH. So what are these terms? So tau is a choice of the trivialization of the contact distribution over each Rabe orbit. I fix such a trivialization for each Rabe orbit. And Q tau is some kind of relative intersection number with respect to tau that only depends on the relative homology class of the current. C tau is a relative first term class, and mu tau is a specific combination of Conley-Zender indices coming from the end asymptotics of this current. And these are more or less essentially topological quantities, and you can check this combination doesn't depend on tau, and it's only dependent on the relative homology class of C. And this is called the ECH index. So what I do after I have such an index, the key inequality that makes ECH work is the following. So you can control the Fredholm index of holomorphic curve with the ECH index. To be precise, if you have a somewhere injective J-holomorphic curve C, then I of C upper bounds the Fredholm index of C. The Fredholm index is geometrically what the dimension of the moduli space the J-holomorphic curve is living in. You can do it slightly better. You can upper bound it by a factor of delta C. Delta C is a count of singularities of C, nodal points, and not etc. And it's always non-negative integer.
If I take C, 2, like C with
so you can also define this thing. You can also define the Fredholm index of C2.
Does it just add, or there's more?
There's some more additive. It doesn't just add. It's not ECH is not linear with respect to this. Okay, so the point is that because of this inequality, essentially, if you require a curve to have ECH index 1, then for generic J, it also must have Fredholm index 1. So this helps you pick out rigid things in the space of all holomorphic curves. So let me just say, like, what goes into this proof. What goes in is understanding intersection theory in 4 dimensions. And specifically, it needs to understand the right of a J-holomorphic curve. So as I draw here, so if you have a holomorphic curve that converges to a Rabe orbit, if you take fixed S, the intersection of a J-holomorphic curve with a slice of the symplectization forms a braid around each Rabe orbit as S goes to infinity. And to understand, so you need to understand the right of these braids to do intersection theory. You need to do it because you're doing intersection theory that's going to infinity. So you have to understand how the curves are behaving at infinity. That's what goes into this proof. So as a consequence of the previous index inequality, you can actually, this is a more precise statement, you can actually use the ECH index to pick out J-holomorphic currents to count. So for a generic J, if you have a J-holomorphic current with ECH index 1, then the current contains a single rigid, non-trivial embedded J-holomorphic curve of multiplicity 1. And everything else is just trivial cylinders of various multiplicities. So this ECH index 1 condition tells you to pick out, you can count, you're basically counting these things. And now with that, you can define the differential. So the differential, if alpha and beta are orbit sets, then the matrix coefficient of the differential is basically a Z2 count of J-holomorphic currents of ECH index 1, positively asymptotic to get alpha and negatively asymptotic to beta. With some work, you can show delta is well defined, basically the Gromov compactness story. And it takes a lot of work to show it squares to zero. The difficulty being that J holomorphic curves can converge to the same orbit set in different ways, as I drawn here. So this means when you try to glue things together, you have to glue a branch cover of trivial cylinder between them to make things match. And this is where the difficulty is. But you can, with maybe around 200 pages of work, you can show this is true. And then you have a homology theory, and you can show this using even more difficult things, gauge theory. This only depends on the contact structure. And this is, in fact, isomorphic to a version of monopole Floer homology. The specific isomorphism is written here. And the point is that once you've established this theory, you can use it and import results from gauge theory to study symplectic geometry. And this isomorphism, or just the general setup of ECH, has a lot of applications to symplectic embeddings, dynamics of rate vector fields, et cetera, et cetera. Okay, so now this is my review of ECH. Are there questions? All right, so hopefully I've convinced you if I give you a contact Riemann manifold, it's a great question of great interest to compute its embedded contact homologies. And as we recalled earlier, to define the ECH chain complex, my orbits have to be non-degenerate. The orbits have to be isolated from each other. But in life, sometimes we're confronted with contact forms that are degenerate with Morse-Bott degeneracies. Let me give you an example. For example, the standard T3 contact structure with rate vector field given by this. I won't do the computation, but you can show the orbits appear in S1 families. So instead of being isolated, the orbits kind of come in, you have an S1 family of periodic orbits, and you actually see these tori that are foliated by Rabe orbits. And we call such S1 families of Rabe orbits Morse-Bott tori. And we'll mostly be concerned with this case in this talk. So suppose you have a Morse-Bott contact form, we can always perturb it to be non-degenerate. And then after we perturb it to be non-degenerate, we can define its ECH chain complex. But it's often very desirable to compute the ECH chain complex purely by thinking about holomorphic curves in a Morse-Bott setting. Because often in the case that when you have Morse-Bott setting, the count of holomorphic curves is easier. So the question is, what kind of things should we count in the Morse-Bott setting to compute embedded contact homology? So let me begin by studying in a bit detail how, suppose you have a given Morse-Bott contact form, how to perturb it into a non-degenerate form. So suppose here you have a Morse-Bott torus, you have these coordinates x, y, z. Z is a Rabe direction, so moving in a z corresponds to moving in a Rabe orbit. X is the direction of the S1 family of Rabe orbits. So if you move to a different x value, you're moving to a different Rabe orbit in this family. And y is a normal direction. So this is a picture to have in mind whenever I say Rabe Morse-Bott torus. And suppose go.
Are you assuming it's always Morse-Bott torus as it's a S1 family?
Yes, always S1 family. I think
it's not higher dimension, like it's not some.
So I'm in 3 dimensions. So if I have 1 dimension,
Okay.
Yeah.
You could have like a top dimension.
Yes, that's done with different techniques by works of Joe Nelson and Morgan Will.
Okay,
And
so
David
these are
Ferris.
one-dimensional families.
Yes.
Okay.
So oops, what did I do? Okay, around this page. So to break the degeneracy, I choose a Morse function with 2 critical points, f from S1 to R. And for delta small, I make the following perturbation. So I take the Morse-Bott contact form, I multiply by e to the delta fx. X here is the Morse-Bott family, is the S1 family of periodic orbits here. That's the x coordinate. Okay. So for delta small enough, all orbits of small enough action are non-degenerate, and they correspond to the critical points of f. So here's my Morse-Bott family, and these are the 2 Rabe orbits that correspond to the critical points of f. And after I perturb, they become 2 non-degenerate Rabe orbits. And one of them is an elliptic, and the other one's hyperbolic. Okay. So again, so let me remind you. So for after I delta small, I can perturb and I get these non-degenerate Rabe orbits, and I compute the ECH chain complex by counting J holomorphic curves. the question is on this side, when I have Rabe orbits, Morse-Bott tori, what is the thing to count? Here I count holomorphic curves. What do I count here? So the answer is that you count cascades. So the notion of cascades first appeared in Bourgeois and Frauenfelder's thesis. So to motivate them, consider the following. Suppose you have a perturbed non-degenerate contact form and non-degenerate Rabe orbits, and you have a holomorphic curve that's symptotic to the Rabe orbits, and we take the limit as delta goes to 0. We take the limit as the size of the perturbation goes to 0, and we consider what the curve C delta degenerate into. And the answer is that if you have bounded energy and genus, it degenerates into a J holomorphic cascade. So I'm going to show you a picture of a cascade, then I'm going to tell you what it is. But yeah, question.
Sorry, I'm just curious if you actually get a chain complex that works like the direct limit as L goes to infinity, or you have to cut your action at any L.
You have to cut off your action at any L, and then you have ECH chain complex defined up to action L.
Yeah.
And then you take L goes to infinity.
But can you talk about like a limiting chain complex?
That I'm not so sure.
Because like the combinatorial picture, like for toric domain
Uh-huh.
and stuff, there is the picture is kind of like a limiting chain complex.
Yeah. So I think the difficulty might be after you small perturbation, so you're up to action L, you have exactly these Rabe orbits, but greater than action L, you may have introduced extra orbits.
Yeah.
And you don't know how to control them.
Yeah, but like in the limit there.
In the limit, you don't have to care about them.
Yeah.
Yeah.
And maybe, I think you're gonna talk about setting up the complex later, right?
Yeah.
So
Yeah,
maybe,
sorry,
maybe it will be
Yeah.
clarified.
Yeah, okay. So I can also talk to you afterwards. Yeah. So okay, where was I? So what is a J holomorphic cascade? So the brief definition is a holomorphic building, and the adjacent holomorphic curves have ends that don't necessarily match, but they match after you take a gradient flow line. So let me show you a picture. So this is a 2-level cascade.
Question?
Yeah.
So in the previous theorem that Yao was you, right?
Yes.
Okay.
Yes. So the horizontal lines correspond to the S1 family of Morse-Bott tori. These are 2 holomorphic curves U and V, and the green lines corresponds to the gradient flows of F, which is a Morse function on the tori. And between U and V, there's a single number T greater than that tells you if I'm at the end of V, how long I have to flow to meet the end of U.
So you're flowing the entire orbit. It's a function. The Morse function is on S1. right?
Yeah.
Sorry, what is T again?
T is a time. It's like to go from this end to this end, I have to follow the gradient flow of F for time T. And between adjacent levels, there's a single number.
So it depends on F or on delta, like it's parameterized.
No, this is,
by delta.
it's not parameterized by anything. This is just a part of the data of a cascade, how long you have to flow.
Okay.
Yeah.
Wait, the T is the same at each level?
In between adjacent levels, there's a single T. So these 2 flow times are the same. And if you have more levels, you can have different T.
Okay, so, there's one T for each red line.
Yeah. And the green diamonds corresponds to the critical points of the Morse function, F. And at the top and the bottom levels, they're connected to these critical points via semi-infinite gradient flow lines. Does that make sense? So this is what a cascade, this is a height 1 2-level cascade.
Does it always start and end at a flow line?
Sorry?
Like,
So this at this point can also start at a critical point.
Okay.
Yeah. So in general, the definition is more involved, but it's essentially just more levels. And between each level, you think of UI living above UI plus 1, and between adjacent levels, there's a number between 0 and infinity inclusive, so that you follow this gradient flow for this amount of time, and then you'll reach the end of the other homologic curve above. And the positive punctures of the top level and the negative punctures of the bottom level are connected to the critical points of that via gradient flows of that. So let me explain how this picture arises. Why do holomorphic curves degenerate into cascades? So I've shown a holomorphic curve that delta is going to 0 in this direction. So you start with a holomorphic curve and its ends are asymptotic to critical points of your function f. And the dotted red lines are where the Morse-Bott tori are. They have been perturbed away, but they're secretly here. And what happens during the what did I do? Sorry. And what happens is that as a holomorphic curve passes close to these Morse-Bott tori, they develop these kind of long, low energy region. And during this low energy region, they will follow the gradient flow of delta times f. And as delta is going to 0, the gradient flow becomes very slow because delta is going to 0. And so the curve has to follow for a very long time. So these necks become very long to go from to travel the same distance. And in the limits, as delta goes to 0, these necks become infinitely long. And you can no longer keep track of them as holomorphic curves, so you keep track of them formally as a gradient trajectory. And then these blue segments will also converge to holomorphic curves. And that's how like a cascade arises from this degeneration.
It's like a breaking.
Sorry?
It's like a breaking.
Yes, it's like a breaking, except there's motion.
So like in C infinity lock on any compact subset of this like green.
It's a trivial cylinder. In C infinity loc, it converges to a trivial cylinder because the gradient flow is very slow.
Yes, which is like the analog of a point of what I'm used to. Okay, yes.
Okay. Yeah.
Yes.
Yeah. Okay.
Okay, so if in C infinity loc that's happening, what's different here?
So in C infinity loc is converging to a trivial cylinder, but in C infinity loc is at each point is converging to the gradient flow of delta f, right?
Oh, and here that gradient flow can change because you're in a family.
The gradient flow is becoming very slow, right?
Yes.
And so as delta goes to 0, the gradient flow becomes vertical in the limit, and this thing becomes infinitely long.
Yeah.
To cover the same distance.
Sorry.
It's like the gradient flow is just constant in the limit. So in C infinity lock, you're just like, you're not going anywhere.
Yes.
And the only way you can recover this like gradient flow line is like not locally, right?
Yeah.
But you could be going along the Morse-Bott, this S1 family, right?
Yeah, you could have like a complete gradient trajectory here.
Uh-huh.
You're moving over here. You're moving in this S1 family in the green region, and T is measuring how far you're moving in the air. Yeah. Okay, so holomorphic curves degenerate into cascades. So you would want to say that if you want to compute ECH in the Morse-Bott setting, we want to count cascades of ECH index 1. So the notion of an ECH index is more or less a topological notion, so you can make sense of it for cascades. So the dream picture will be something like this. So as delta is positive, you have these straight holomorphic curves, and as you degenerate to delta equals 0, they degenerate into a one-to-one fashion into these cascades. So to compute the chain complex, you can just count these cascades. And this picture doesn't always work for the following reasons. So there's these following difficulties. So first of all, when you have a sequence of holomorphic curves degenerate into a cascade, it's kind of like a SFT type degeneration. So the levels can have multiple covers, and that ruins transversality for you. Problem number 2 is that let's pretend problem 1 doesn't happen. Let's pretend all the curves are somewhere injective. So what happens is that between cascades, there's a single number that says the ends have to meet each other up to flow in T. And this is best formulated in a fiber product. And even if all these curves are somewhere injective, the fiber product might not be transversely cut out. And this is the more serious issue. And number 3, let's pretend that 2 issues don't happen. So can we actually make precise there's a correspondence between cascades and J-homomorphic curves after you perturb a little bit? So I addressed some of these in the following theorems. So the first 2 bullet points, the first 2 points are basically the moduli space of cascades need not be well behaved. And the final bullet point is, can I construct a correspondence between the moduli space of cascades and moduli space of holomorphic curves? So let's answer the first bullet points. So if you have a contact 3 manifold, and this is where ECH index comes to the rescue somewhat. So if you have a Morse-Bott contact form, so after a generic choice of J, the space of Cascades with EC index 1 and genus 0 is discrete, finite, and transversely cut out. So, but only for curves of genus 0. There's more things you can say, like for after there's more stuff you can say, but this is the cleanest statement that can come out. You can say like for Cascades with less or equal to 3 levels for generic J, ECH index 1s are transversely cut out, et cetera, et cetera. But this is the one I'm going to talk about today. And this is the gluing theorem. The some version of the theorem first appeared in Bourgeois' thesis, and then there's Bourgeois and Noanchas who did symplectic homology, and then there's this paper I posted this year, which uses kind of different gluing techniques and took about 100 pages. But this addresses the third bullet point, which is you have a J-homomorphic curve that's transversely cut out and rigid. Then after a small perturbation, it can be glued uniquely to a J-homomorphic curve up to translation in a symplectization direction. Okay, so combined with the previous theorem, we can now compute ECH using Cascades in certain cases. So if you have a contact manifold with Morse-Bott contact form, if after some small perturbation, all your ECH index 1 curves already have genus 0, then you can compute the ECH homology by counting ECH index 1 genus 0 cascades. This is just the convex span of the previous 2 theorems.
What examples are for when we know that the index 1 curves are genus 0?
This slide.
Oh.
So, yeah, question.
Can you just go back?
Yeah.
Do you mean to say lambda delta converges to lambda?
Yes, thank you. Yes. 0 converges to 1.
And can you go back one more?
Yeah.
Can I ask my question again?
Yeah.
So are you saying that with this condition of genus 0,
Yeah.
that there is a chain complex whose differential counts these cascades and whose homology is exactly the ECH non-filtered? It seems that that's the corollary.
Yeah, so there's like for up to action L, there's like a 1-to-1 correspondence between the chain complexes up to action L.
Sure.
I think you can just directly take the limit as you can do that, but I haven't thought too much about it.
Sorry, you're just saying the homology is the same.
I'm saying that differentials are the same.
You're saying so sorry.
He's saying like differential up to action L is the same, and then you can take limit over homology, right?
Yeah.
I see.
Yeah.
But you're not saying that because your chain complex is defined for every L, right?
Yes.
Yeah, so, but you're not saying that this. No, you are saying that this complex when you take the.
Yes, I think so. But
sides on the nose.
yes. I think so.
Okay.
But I haven't thought too hard about it, so take it with a grain of salt.
What is the ECH index of a cascade?
So all of the terms I had, relative intersection and Chern class and Koenig-Zünder indices, these are only depends on like in the definition of the ECH chain complex.
Yeah.
They only depend on relative homology classes. So what you see a cascade, you should glue in for segments of trivial cylinders, just glue in a cylinder.
Okay.
And then that defines a relative homology class. And then you can take its ECH index. Okay, so when does this actually happen? First of all, it works for T3. It works for T2 bundles over S1. This is Eli Bo's thesis. And then it also applies to boundaries of concave and convex toric domains, which we describe briefly below.
Sorry, do you mean Choi?
Choi,
Oh.
yeah. They have a weird rendition of how the references come up.
Oh.
Yeah, this is Choi. Yeah, this is Choi.
And what's the first one? That's the full name?
T3.
No, Leb.
Lebow, Lebow.
Okay.
Yeah. Okay, so consider the moment map from the T2 action on C2. If you don't know what the moment map is, just look at this map. Okay, so if you choose a smooth function from 0 to 2, 0 to A to 0 to B with 0 mapping to B and A mapping to 0. I'll show you a graph of this function on the next slide. And let gamma F denote the graph, and let delta f denote the region bounded by the graph and the xy axis. I'll show you a picture. So this is my function, this is my graph of function f, and delta f is the shaded purple region. So if this region is convex, then its pre-image is called a convex toric domain. And if this is concave, its pre-image is called a concave toric domain. So this is a convex toric domain, concave toric domain. In any case, you need to add in a bit more technical conditions, but its pre-image of the graph is a contact 3 manifold with a Morse-Bott contact 1. Yeah.
So here you're not asking that when you reflect this domain, you have something convex, right?
I think you should do that. I mean, my graph, the function should be roughly linear on these edges.
Okay.
But he's saying that like there's two definitions of convex toric.
Yeah,
I mean, there's
yeah.
the one where it's convex if you take it, if it's reflection across everything, and there's the one where it's just convex.
Let me take the more strict definition.
There is microvex.
Yeah. I'll take the more strict microvex definition.
Yeah, so f is a concave function.
Yeah, exactly. Yes.
A decreasing concave function.
Yeah. So what are the Rabe orbits of this contact 3 manifold? There are two elliptic Rabe orbits corresponding to the intersection of f with the xy axes. And for each x where the slope is rational, this pre-image under the moment map is a Morse-Bott torus. And there's some topology calculations. I should probably also put Conchoy somewhere. If we perturb the way Morse-Bott degeneracies, then all ECH index 1 curves have genus 0. Hence, these are a large family of domains where you can compute the ECH chain complex by enumeration of cascades. Yeah.
So I think that, I mean, I'm not sure.
Uh-huh.
I think using con stuff, you could probably do that for all star-shaped toric domains, not just.
Yeah, I haven't read his thesis carefully enough to know that's the case, but potentially yes. Yeah.
I think like if you go beyond convex,
Uh-huh.
if you include concave,
Uh-huh.
I think if you believe that he can do it for concave, I'm not 100% sure, but I think that it's not a lot easier to just do only concave, but if it's partly concave and partly convex,
Okay.
I could be wrong, but.
Okay. Yeah. Okay. So now I give you a sketch of the gluing. So let's remind ourselves what's our goal. Given a transversely cut out and rigid cascade, after we perturb for small enough, I want to glue it to a J delta homomorphic curve. And I'm going to use the gluing setup from Hutchings and Taubes in their obstruction bundle gluing paper. And the strategy is we try to, as much as possible, separate the dynamics over the gradient trajectory segments from the dynamics of a J homomorphic curve segments of a cascade. And I'll explain a little bit why in the next slide. But the specific strategy is we write down the PDE for each gradient flow segment, and we write down the PDE for each J homomorphic curve appearing in the cascade. And finding a gluing is equivalent to solving a system of nonlinear differential equations. So let me describe what kind of the difficulty of this construction is. So imagine you see a 2-level cascade and you try to glue it. And first thing you notice is that you're gluing in a scenario where there's less transversality than usual. So usually when you have two homomorphic curves meeting along some manifold, you require their evaluation maps to be transverse in order to glue. But here I'm asking less. I'm saying they're transverse up to this translation in the gradient flow direction. So there's kind of less transversality than you would usually do for gluing. And the second difficulty is that then you say, okay, I can still do it. I'll just maybe do some more detailed argument. And the next technical difficulty is that somehow like the homomorphic curves and the gradient trajectories behave kind of very differently. Things happen on different scales. And to be precise, a vector field from the perspective of the homomorphic curves that's very small can look very large when you try to put in a gradient trajectory. So let me be more precise. So here you have U and V. And here, after you perturb, you've tried to fit in a gradient trajectory of length T over delta, because the gradient flow is of speed delta. So the length of this gradient trajectory is T over delta. Now you imagine slightly displacing this end by just slightly to T prime. And this is from a perspective of V, this is kind of a small displacement. You moved it only a little bit. But then you try to fit another gradient trajectory and that's of t prime over delta. So a small change in t from the perspective v is a very small change, but after you try to fit a gradient trajectory between them, the length of this increases by t minus t prime over delta, which is going to infinity as delta goes to 0. So that's kind of like the technical thing you have to really control how these equations are coupled to each other as you change these things around. And that's the main difficulty. So let me try to explain to you what kind of a general strategy is in Hutchings and Taubes. So I'm doing okay. So here's a toy example. I'm going to try to glue a trivial cylinder to a trivial cylinder. So forget everything I've said in this talk. Imagine you have a non-degenerate ray orbit and you have two trivial cylinders, and we want to glue them together using Hutchings and Taubes framework. And I'm doing this example to illustrate how the machinery there is set up. And so let's say you have two trivial cylinders, U and V, and they've drawn here, and have a gluing parameter R. And I choose cutoff function beta U that's constant up to where the pre-gluing happens, and then cuts off very slowly. That's beta U. And I have beta V, which is constant along V, and then slowly tapers off as it leaves as it enters this region over here. So let's U hash, this is called hash or sharp. What's the sharp?
That's a hash.
Okay, U hash V denote the pre-gluing of U and V. And then I'm going to try to deform this pre-gluing. Let's pretend I didn't know that this pre-gluing is already J holomorphic. I'm going to try to deform this pre-gluing and try to make it holomorphic. So there's more bells and whistles here. I should use weighted Sobolev spaces and more things to put in here. But let me just, for simplicity, let's just take a vector field psi of U and psi of V. And psi of U is my deformation of U, and psi of V is my deformation of V. So we try to deform the pre-glue curve with beta U psi U. So that's psi of U cut off after this region. And I try to then plus beta V psi of V, which is psi of V, which is, and then cut off as it enters this region. So I deform the pre-glue curve with this vector field and ask, when is the resulting thing J holomorphic? So this equation can be written in this form. So theta U is an equation, you should think of theta U as an equation living over U, and theta V is an equation that's living over V. And what do these equations look like? Well, theta U looks like the linearization across of U applied to psi of U plus some cross terms from coming psi of V plus some nonlinear terms. And similarly, theta V is linearized equation applied to psi of V plus some cross terms coming from psi of U and plus some nonlinear terms. And I've chosen my cutoff function so that the parts of psi of V that goes into theta of U is supported near U. So theta of U only sees the part of psi V that's close to U, and similarly for theta V. So if I can solve this system of PDEs, theta U equals 0, theta V is equal to 0, then I can find this thing is equal to 0, and I can find the gluing of my original problem. Any questions?
I know you said forget about the rest of your talk, but when you're gluing these cascades, are you taking sort of the cylinder along that gradient flow and
Yes.
then gluing?
Yes,
Okay.
a very slow cylinder.
So one of the U's will be that.
I'll explain how to do that later, after I'm done with this toy example.
What are the F's again?
They're nonlinear terms, so they're quadratic in each of these inputs.
Oh, okay.
So they're
The
not,
coupling is only in these terms, right?
and this cross term,
Oh, this is cross term, okay.
because this is
Yeah.
theta U, yeah.
Understood.
Yeah. Okay, so I'm going to try to solve this system of two PDEs. So how am I going to do that? First, I'm going to fix psi of U. Okay, I fix it to be small, and then I'm going to solve theta of V. After I fix this one, the only independent variable is psi of U now, right? So this is done with a contraction mapping principle. Let Q of U be a right inverse to D of V. So Q of V be a right inverse d of v, and then this map has a fixed point, and therefore this equation has a solution. And it's not so hard to show this map has a fixed point, essentially because this part is quadratic and this coefficient beta prime is very small. So this map has a fixed point and it's a contraction map. It's a contraction mapping and therefore has a fixed point. It has a unique fixed point, and this I call this fixed point psi of v bracket psi of u because so this fixed point depends on the psi of u I fixed. Does that make sense? Now I'm going to plug this psi of v into my other equation. So we plug this into psi of u. So now psi of u, the only independent variable is just psi of u. So I try to solve it by another contraction mapping. I find a fixed point of this map. And here's my psi of v depends on psi of u now. But you can show this is kind of like a nice kind of dependence. Like the derivatives are bounded, and this is also a contraction mapping. Make sense? And then afterwards, we have solved the system equations and we have a gluing. That's kind of how like gluing works in the Hutchings and Taubes framework.
And so how is this different from the usual like Picard iteration kind of?
I think the usual you do a pre-gluing of the entire space and perturb along the vector fields of the entire space. Here you're kind of trying to separate what's happening over each holomorphic curve separately.
Okay.
Philosophically, they're doing the same kind of thing, but this way.
So the difference should just be like I'm doing kind of Picard iteration on two separate things as opposed to Picard. Is there a reason why you can't like do it in the usual?
I couldn't do it for the Cascades. I couldn't do it in the usual thing. I had to separate and study how the equations couple together.
Okay, I can ask questions.
Yeah, sure. Yeah. Okay, so let's do a simple case of the more general case. So let's imagine we have a holomorphic curve and let's connect it to a semi-infinite gradient trajectory. So this is my holomorphic curve u, and then here it's connected by a gradient trajectory to a critical point of f. So let's do the gluing in this case. So this is gluing of one level cascades. So let's suppose, so that's the setup. So what is the appropriate space of deformations of u? So it's still, I'm dropping some things, but essentially still consider a vector field psi of u and the asymptotically constant vector field that's asymptotically constant to x, which is the Morse-Bott direction. So if you have, this is the blue is in u and u plus p dx is like asymptotically shifting this neck horizontally.
P can be negative. Also.
Yeah, P can also be negative. So your space of deformation consists of two kinds of deformations. One is psi of u, the other is this asymptotically constant vector field. Does that make sense?
It's psi of u is asymptotically constant.
No, psi of u is in W2P.
So that's like moving the entire thing?
No, psi of u is like, it's kind of asymptotically zero.
Oh,
right?
Okay.
Yeah. Okay. So what I'm going to do is that for each pair of psi u and p, we pre-glue a gradient trajectory Vp to the curve u plus p dx. So another way to say this, for each value of p, I choose a different pre-gluer. So if I just had u, I would pre-glue to this gradient trajectory. But for a value of p that's non-zero, I move the end of u by p and then pre-glue to a different gradient trajectory starting over here. Does that make sense?
Sorry, can you repeat that?
So for each pair psi u and p, which is a space of deformations of u, I pre-glue a gradient trajectory to u plus p dx. So if everything was zero, I would just pre-glue I would take u and would just take a gradient flow from here. For non-zero values of p, u plus px corresponds to moving this end. P. What is p? P is this p. So the space of deformations of u consists of vector field and then a vector that moves its neck.
And sorry, what's dx?
Dx is a vector field that's pointing in this direction.
So it's like the gradient direction.
Yeah, it's a gradient direction.
Yes.
Yeah.
And phi is just how big the
Yes. How much you're moving in this direction.
So you kind of want to displace the orbit inside the Morse-Bott
Yes.
before you.
Yes.
Right, and this green cylinders in the next picture,
Yeah.
those are not trivial cylinders.
No, they're gradient trajectories, very long gradient trajectories. Okay, so after you fix a pair, so you pre-glue a gradient trajectory U plus P to U plus P dx. So this is, I'll call this VP.
So some part of VP is V, right? Like if.
Eventually, this will catch up to V, yes.
It will
Yes.
catch up,
Yeah,
right?
yeah. But that's not how I'm thinking about it. I'm thinking about this infinitely.
Separate, okay,
Yeah,
fine.
yeah. Okay, so then we try to run the same story as before. So given a fixed VP, let phi of P be a vector field that deforms VP. And then consider the pre-glue curve, U plus P dx hash VP, that's this curve. And then I deform this pre-glue curve using these vector fields. Theta U psi of U plus beta V psi of, these two phi are the same. These two, this is a typo, phi of P here. And I try to consider this deformation. I ask myself, when is this deformation going to be J-homomorphic? And this splits into two equations. Theta U, which is living over U here, and theta VP, which is living over VP over here. And P is implicit, but as I change P, this whole thing changes. Does that make sense? Okay, I lost everyone? Okay, good. So then for fixed psi U and P, the equation over the gradient trajectory has a unique solution, which depends on P and psi of U.
Great question.
Yeah.
So when you're changing P, are you also imagining that the domain is changing or
So-
keeping that fixed?
So the domain here is always going to be a half infinite cylinder.
So you're imagining that that's fixed?
Yeah, that's
Yeah,
fixed.
okay.
Yeah.
So that's why like this thing, when you have a psi U, that always lives over a half cylinder.
Yeah, yes.
Okay, got it.
Yeah. So for fixed psi U and P, the solution over this always has a unique solution. And I'll denote it by phi of P psi of U. And I know so we next vary psi of U and P as inputs to theta of U. So as we vary P, we're changing the pre-gluing by a lot as well, but via parallel transport, all these vector fields can be identified. So the point is that the vector field phi of P varies nicely with P. As you vary this pre-gluing, after these identifications, it doesn't change by a lot. At least it changes very controlled fashion. So now you know this function depends on P and psi U in a nice fashion, and then you can consider these as your input variables and apply the contraction mapping principle to this equation. And therefore, there is a gluing. Are there questions? Okay, so let me explain at least a little bit the case of,
I have a question.
yeah.
Is there's no, like all of these DUs and stuff are transverse.
So DU is surjective.
Yeah.
Yeah, all of them are surjective.
Okay. So even for the other equation.
Yeah.
theta V-
But if you set it up correctly, this one is also surjective.
I think I lost some of the big picture. So you said that you have this problem that when you change T a little bit, actually T over delta changes by a lot.
Yeah.
How is this?
This doesn't come into this picture yet.
Oh, okay.
I'm gonna get to it in the next slide. So the question of this is, maybe I should use the board because I didn't put this in the slide. So the case of gluing higher level cascades is much harder. And for this reason that, so you look at this and you can write down three equations also, theta U, theta V, and theta for the gradient flow. And each of these UV, you can move these ends together. Move these ends like in separate directions. And when you move those ends, you're changing the pre-gluing very drastically. Does that make sense? So let me write.
Yeah, what happens if you restrict to moving them in the same direction?
Then you'll not get enough surjectivity. You're reducing your domain, you'll not get enough surjective operators. So here's your U. here's your V, and this is your gradient trajectory G. So you have PV, which moves this end, and PU, which moves this end. Imagine if you move them in the opposite direction, you're lengthening the gradient trajectory by a lot. So what happens is that you can still write a system of three equations, theta U equals 0, theta V is equal to 0, and theta G is equal to 0. So for given fixed input, you can always solve this equation over here. You can always solve this equation in the middle segment here. But what happens is that as you move these ends, you're drastically changing like the domain of the middle.
Like the bound and the derivative that you need to solve the coupled ones?
Yes, yes, you have to bound how as you move, how these equation feeds back into this equation.
Like the theta U of theta G, that one.
Theta, so the solution
Once
here.
you solve for theta G. Oh, that's.
Yeah, so you need to control this derivative. dp.
What PU?
So as you, for fixed,
What is PU?
PU is like the horizontal displacement of U.
Okay.
And you need to control how this term feeds back into these two terms.
Okay.
And the way to think about it is to better understand the equation you constructed in the middle. So this cylinder is very long. So you should think of it as being like doing something here, then exponentially decaying towards the middle. And doing this is for theta P, it does something here, then exponentially decays towards the middle. So you
want to break it into two half cylinders?
Yes, you break it into two half infinite cylinders. And then essentially for half infinite cylinders, it will begin to look like the solution for semi-infinite gradient trajectories. Then you use you write this as like the sum of two solutions for two semi-infinite gradient trajectories plus some error term. And this, you understand how they feed into these two equations. And this error term, because of exponentially decay, is exponentially suppressed. So it feeds these into equations into this in a controlled manner as well. Okay. Maybe I lost people.
Okay, so you're saying that you sort of want the cylinders to move to each other, not away from each other?
You can, no, you're trying to, the cylinders can move in this way.
Yeah.
And you're trying to understand how these equations are coupled to each other during this kind of motion.
But like the gluing does the gluing only happen for one set of these parameters or for both? Like do you need it to?
So you have this so you have PU and PV, right? And this controls how you're doing the pre-gluing.
And like if the PU and PV are such that these are sort of moving away from each other, do you still get?
So this, I'll say it like this. These two, the space of possible PU and PV lives in a disk, right?
In a disk. Oh, yeah.
Yeah. And for a particular point on this disk, there's going to be a gluing for the entire cascade.
For only a particular?
Yes, for only particular choice of PU and
that's why
PV.
it's a unique gluer.
Yeah.
Okay.
Yeah. Okay. Does that answer your question?
Yes.
Okay. So then, yeah, basically you kind of need to control how the thetas are coupled to each other, and you need to do a second gluing, pre-gluing, basically what I wrote over there, to control how the coupling works. And then once that is established, there's a standard argument from Hutchings and Taubes to show the gluing is unique. That's all I had. Thank you. Question?
Oh, questions. I was, sorry. Any questions?
We had a lot of questions during the talk.
Yeah.
So we might be out of.
I have one question.
Okay, yeah.
So you don't, it sounds like one shouldn't expect these methods to work for like contact homology because we don't have the ECH index to save us, right?
So yeah, so like the contact homology might not work because your U and V might be not transversely cut out during the degeneration process. But if you can show somehow these are transversely cut out, actually in contact homology, because your gene is 0, that that's all, basically that's all you need. Yeah.
Do you think that if you had a situation where you had Morse-Bott families that were not S1,
Uh-huh.
Yeah, that was the.
I think it could work. Yeah.
it could work.
Yeah, I think there's no, it's a question of linear algebra, basically. There's no further, I don't expect any difficulties.
So like you're saying like a
I guess-
full dimensional Morse-Bott family, that kind of.
Yeah,
Yeah.
that's probably the only other.
So for full dimension, there's a difficult. You can probably show you can use cascades to compute a chain complex, but what's then difficult is like, what are these cascades? I know like Joe Nelson Morgan's Weiler's work is basically saying, no, there's no higher genus curves that contribute. And that's the non-trivial part that you don't get from this.
Yeah.
Here's a question.
Yeah.
So the UMAP, so let's say I wanted to do a Morse-Bott calculation of the UMAP. I think this is like pretty difficult in the S1, in like the case where you have a full like if you have an S1 bundle or like that's it turns out my impression is that the differential in, for instance, that case is pretty well understood, but like the UMAP is actually pretty hard to calculate with cascades. So I don't know if you have any like insight into that.
So I can tell you what the main difficulty is. Like you have to show the cascades counted by the UMAP are transversely cut out. There's no multiple covers, and there's no, and even if there's higher genus, they don't. Basically, you have to control for. You have to argue the moduli space of cascades is well behaved, and then the gluing should also just come in as here.
Yeah, the Nelson-Weiler argument to rule out higher genus UMAP curves, I think.
Yes.
Or higher genus curves from the UMAP doesn't work.
Okay.
It doesn't fit a differential.
I see.
As far as I recall.
Okay. So there, as I said, that
You were saying it doesn't work?
Yeah, I think so.
so.
Like, you know what the genus 0 curves are, but.
So aside from genus 0, there's more things you can put here that will still make this statement true that I write more carefully in this, but this is the main obstruction. How do you make sure the space of cascades is a well-defined, well-behaved object? Yeah.
Is it actually easier to count cascades compared to?
Well, sometimes. So basically like the computation with T3 Michael did. So I think how it worked is he imported a bunch of homomorphic curves that Taubes found in the Morse-Bott setting, and then he put them into cascades.
So actually, question. So like, is that paper rigorous without something like this? Like that, like meaning like, did he actually avoid, was the Morse-Bott theory of that paper just motivational and he actually had a way of computing? I've never read that paper. So
What paper?
this paper, it's like the original,
I think
basically.
so.
The Bourgeois paper? you mean?
Well, no. So it's so
Rounding
Michael had this
corners.
paper where he basically
Oh, my.
computed
Yeah,
the,
Hutchings-Sullivan.
this Hutchings-Sullivan paper. It was like the first calculation of like a non-trivial kind of ECH complex or PFH type complex. And in that paper, I remember them like kind of invoking some Morse-Bott theory.
Yeah.
In that paper, but I don't remember. I never read it in detail enough.
I thought they needed some kind of correspondence, but I don't know for.
So they used a correspondence, but is it a correspondence that requires like your paper, or is it like, meaning like, are you kind of patching that, or?
I think, I suspect so. I should check more.
That seems like a pretty good motivation for this, since that paper was so kind of seminal in the whole area. So.
I think that it's rigorous. I mean, as far as I remember.
Okay.
Yeah, like the Dane twist paper.
Yeah, that one.
Using the Thomas's sort of homomorphic beasts.
Yeah.
Yeah, I mean, it's like.
I can double check on that.
Yeah, that's an interesting, because I think that's a really nice motivation for fixing all of this. You know? Anyway, maybe that's a good place to stop. So
Yeah.
let's take our speaker again.
Okay.